Okay, so thanks for your feedback. So I adapted a bit the content, and I planned a second part, which is not this one. I can make the slides available, so I just decided to slow down a bit to recap something that I did yesterday and present the content through which I went a bit very fast yesterday, and Felix supposed that I already went through it, which is not the case, so I felt guilty after that, right? So let's go slower, and if you're interested in the second part, which is more advanced on the core spaces, you can have a look at the slides and at the relevant chapter in the book, okay? So this is just a disclaimer. So if you still don't hear me, please let me know. I try to make some efforts. My voice is not very loud. Okay, so first a little recap about what I did yesterday. So I introduced the additive Schwartz method. So here is the recap about the algebraic version. So here you want to solve the discretized, let's say, Poisson problem, the linear system AU equal F, defined on such a domain. Okay, now if you want a decomposition of the domains, you can see that the decomposition of the degrees of freedom in two subsets of degrees of freedom. And you can define the matrices Ri, which are restriction matrices, from the global set of degrees of freedom into the local set of degrees of freedom. Okay, so then the algebraic form of the Schwartz algorithm can be written this way. So this is the local version. So what I denote by uj is the local vector, unknown vector, corresponding to the subdomain omega j, okay? And the Schwartz algorithm is written in this way. So I compute the m+1 iteration of this vector from the mth iteration by solving local problem in parallel. And how is it written at the algebraic level? So here I just compute the global residual. So this is just the algebraic rewriting that I explained yesterday. You have the global residual, you restrict it locally to a domain, you solve the local problem, and then you update the local solution, right? And now this is a local writing. So if you want to have something nicer global, then you just write that this uj is the restriction of the global unknown vector, and you introduce, okay, this notation. These are local matrices, local Dirichlet matrices, and these are computed from the global matrix by using the restriction extension operator. Okay, so as you have understood, so domain decomposition methods are a divide and conquer type of methods. So we have divided, but we need yet to conquer. So here first notice that you have duplicated unknowns. So in the overlap you have double versions of the unknown vectors. So that's why you need a partition of unity here. So partition of unity, it's simply a matrix such that this relation holds, and this ensures that you don't put too many information. So here I just put 1/2, because if you have one unknown that belongs to two domains, you can imagine that this partition of unity contains 1/2 on the diagonal. Okay, so after having computed the local contributions, that you apply the partition of unity, you extend, and you have reconstructed here the global solution. Okay, so this is the Schwartz algebraic version of the Schwartz method, and this is exactly the discretized version of the original Schwartz method, the continuous one that I showed in the very beginning. And this also bears the name, was introduced by Kai and Sarkis 1999, which is called RAST, Restricted Additive Schwartz. So now there is another thing. So you will see that after rewriting everything at the global level, that means you update the solution at the iterate n by, as I said, you apply the restriction to the residual, you solve internally, and you extend, right? And you can introduce a notation here, this m-1 RAS, which is this quantity here, right? So you just sum up of the restriction, local solve, partition of unity, extend, right? And this is exactly, it's something that is a preconditioner that comes out for free from the decomposition into subdomains, even if here we have a stationary method. So this is a summary of what I did yesterday. So hopefully this makes things a bit clearer for you. So now I just move on. And as I said, you can define this stationary method in which you have the preconditioner for free. But now the question is, I don't fully like this because it's non-symmetric, you see. So here, even if the local matrix is symmetric, since you put the partition unity only on one side, this quantity, this matrix is non-symmetric, right? So in fact, you have a stationary precondition iteration in which the preconditioner is non-symmetric even if the matrix is symmetric. So this is not nice in general for the sake of theory. So people have invented symmetric variants of this, and you just drop the partition of unity, so you have the additive Schwartz. Or you can be more democratic and say, okay, since I have the partition unity at the left, I just add it to the right, and this is also a symmetrized version of this. And you can do even more. So since a preconditioner anyway, which I explain a bit later, the notion of preconditioner. So a solver, that means you solve iteratively something. A preconditioner needs to be only an approximate inverse to a matrix. So that means you can put something else here, not necessarily the local matrix to the subdomains. So now you have this method. You have a stationary method in which you can put different variants. So now the question is, which one is better? How do they converge? Can we say something about the convergence, right? So this is the whole world of domain decomposition methods. So I won't show very sophisticated convergence proofs because it's not the scope of this school and I don't have the time. But just to mention that the symmetric version are easier amenable to theory, whereas for this one, there are only very, very recent results on the convergence theory of the Schwartz algorithms. Okay, so now I move on to, as I said, I won't claim I will do very complicated theoretical convergence proofs, but I will show you just two examples in which I can say something about the convergence of these algorithms. Okay, so these examples, so first of all, one, it's a very easy one in one dimension. So in one dimensional case, I can literally compute everything. I can compute errors, solutions, and I can see exactly how the iteration goes. And then also I can do some similar computations in two dimensions, but I need another tool, which is the Fourier Analysis. Okay? Why I explain this here? Because they are very easy to explain. They do not require the introduction of very sophisticated tools, mathematical tools, but you can find a lot more in the relevant literature. So let's look at this analysis in one dimension, right? So now what is the relation with respect to what you have seen just before? So we just want to analyze the purely iterative Schwartz method, so the original one, in its original version, that means alternating version, not fully parallel. But you can do exactly the same thing for the fully parallel version, right? So let's start by the one-dimensional case. So I take just an interval, which is my domain, which is this interval 0L. I decompose it into two subdomains which overlap, okay? And now I just want to compute how the error will decrease throughout the iterations, right? So I compute the error in one domain, in second domain, I write the interface iteration, and I want to see what is the reduction of the error throughout the iterations, right? So now, since I'm working here with the one-dimensional case, so this is my Laplace problem. So that means the error vector here, error vector EIN, is the error in the subdomain I at the iteration n. So this is just the local solution minus the restriction of the global solution. And so that means the error will verify the homogeneous counterpart of the PDE, which here is a ODE, right? So this is my Laplace in 1D. This is the boundary condition at the left boundary here. And this is the interface conditions because the domain omega 1, it's 0L1. So here, this domain, this will take the information that comes from the domain 2 at the previous iterate, right? So this is just a one-dimensional ODE for which you can compute exactly the solution. I just try this for the domain 2, for the domain 1, sorry. For domain 2, it's exactly the same thing, but the other way around, right? You have a 0 which is in L, and you have this iteration in small l2, okay? So if you look closer to this, these are harmonic functions. So in 1D, they simply are linear functions, affine functions that verify some boundary conditions. So you can compute everything. So this is in the second domain, the same thing as I told you. And now let's compute the solutions, right? So if you compute the solutions, you see they are, as I said, they are affine functions verifying the zero boundary conditions. For the first domain is 0 on the left, for the second domain is 0 on the right. And they also verify the interface conditions, right? So if I were to write the exact solution, so in the first domain, you see it's x over L1. So that means it's clearly 0 in x equals 0. And this will verify if x is equal L1, it's exactly equal to E2 and L1. So this is exactly the first interface condition. Now for the second domain, it's just L minus x, L minus L2. So you can see here that if x equal L, this is 0. And if x is equal L2, it will verify the boundary condition, okay? So here you can iterate then. You can iterate in L1. And then you can iterate in L2. And after you do all the computations, are very simple 1D computations, then you can deduce from here that the error in the domain 2 at the iterate n plus 1 at the interface L1, it's some quantity that multiplies the error in the same domain at the iteration n. So this quantity here, which is a bit ugly, but you don't have to look at it, is simply the reduction of the error between the iteration at the interface. So this is a measure of the convergence of the algorithm. So all you need to retain from here is that the errors are computable, and you can compute also the reduction of the error between the iterations, right? So what do you want to say? So how can you conclude from here? So obviously the algorithm will be convergent if the factor here is less than 1. That means if there is a reduction of the error between the iterations, right? So if you look closer here, there are a few terms involved. So this is delta being the overlap between domains. And you have capital L and L2. So these are positive quantities. So you see that sufficient conditions to have this strictly less than 1 is that delta is bigger than 0, strictly bigger than 0. So that means that if the overlap is non-zero, this is a sufficient and necessary condition to have convergence. So I hope this is clear. So now this is a graphical representation that what you have just seen of all these computations and what I've just computed, right? So let's have a look at it. You have the domain 0L. 0L1 is the first domain, L2L is the second domain. I start with the initial guess, which is this E2 naught. I compute the error in the first domain, which is E11. And then I give the error here at this interface to the second domain, which will compute the solution here. And it will transmit the solution to the first domain, it will compute again the solution, and so on, right? So you see that the error will decrease, as the iteration go, right? And this decrease is made possible because of this overlap here. So as a first conclusion, so this kind of algorithm needs an overlap to be convergent. And also the bigger the overlap, you can see already from here, the faster the convergence of the algorithm. So now you might say, okay, this is 1D, so what can I do in 2 dimensions? Also in a very simple way. So a very nice tool, it's Fourier Analysis. So obviously you cannot compute exactly a solution in 2-dimensional case if you have boundaries and irregular domains, right? This is not possible. You can do it in very particular cases, but a very nice way to see it is just to say, my domain is simply R2, it's the whole plane. I decompose it into 2 infinite domains which overlap. So you have the first domain, it's bounded only in x direction here, so it's minus infinity delta. The second domain is 0 infinity r, right? So you see that they overlap and the overlap is defined by this parameter delta, but otherwise they don't have boundaries, they're infinite domains, right? So now what do? So you want to, again, to quantify the convergence of the algorithm. So to quantify some convergence factor, so that means to define a quantity that's a measure of the convergence of the algorithm in a very simple way. So that means you need, again, to write the equations verified by the local errors. So again, you put the local errors will verify the homogeneous counterpart of your PDE. You have interface conditions, but here you don't have boundaries, because the domain is unbounded, but still you want your error, local error, to be bounded at infinity. So this is the only condition that you put there, okay? So the same in the second domain. So it's not the same infinity, so the first domain it's minus infinity, the second domain is plus infinity. So now how do you compute the errors here? So here you use a very nice tool, it's use the Fourier transform, but not a full Fourier transform, just a Fourier transform in the y direction. Why y direction? Because in y direction your domain it's infinite, and the x direction the domain is bounded. So just a partial Fourier transform in y direction. So that means you just write the Fourier, you denote by ej hat the Fourier transform of the error, the local one, right? So that means the partial derivative in y will be replaced by ik times the Fourier transform. So the second order derivative is plus k squared, right? So this is will replace the second order partial derivative in y. So now that means your PDE will be transformed into an ODE. And here this ODE will depend on k. So for any given frequency k, you can compute here the local solution, okay? Which is the Fourier transform of my local solution, okay? So this is a very simple second order ODE. You can compute it. It's just a combination of exponential. So here it's a glitch here. It's a problem. There should be an exponential here, exponential of lambda plus, right? So it's a linear combination of two exponentials with real and with the negative and positive parts here. And you need to impose the condition that the error should be bounded at infinity. So as usual, when you solve this kind of problem, you have one exponential which is increasing to infinity and the other with decreasing to 0, okay? So that means you'll keep only the exponential that is vanishing, not the one that is increasing to infinity. So obviously, since your domain one, it goes to minus infinity, the other goes to plus infinity, you will keep for each domain a different exponential here. Okay, so this is what I just said. So the Fourier transform of the error in the first domain, it's simply this coefficient times the exponential of the symbol here, which is positive, and here in the second domain with the exponential of the symbol, which is negative. So you see that this will tend to 0 as x goes to minus infinity, and this will tend to 0 as x goes to infinity. So to summarize, by using the Fourier transform, I was able to compute the local errors. Then I can iterate at the interface, and the same way as I did in the one-dimensional case, I can write the iteration at the interface. I can compute these coefficients here, and then these coefficients will decrease with a certain quantity here between the iterations, right? So don't pay attention too much to all the details of the notations, but just keep in mind the general idea. So the general idea, you solve an ODE, you iterate the solution, you compute the coefficients, and the iteration of the coefficient will give you this. And this quantity that you have here, I call it convergence factor, and this will give me a measure of the convergence of the algorithm. Obviously, if this is less than 1, the algorithm will be convergent. If it's bigger than 1 or 1, that means the algorithm is not convergent, but it's not good. So again, in this very simple case, this quantity is computable, and it has this very nice expression. Right, so this is my convergence factor, and depends here, just have a look at all these things. So it depends on the overlap delta, it depends on the frequency k, and here eta, it comes from the equation, right? So we can, so let's have a look at this quantity here again. You can see clearly that this is strictly less than 1, when delta is positive, strictly positive. If delta is equal to 0, so you have 0 overlap, this will be equal to 1, so algorithm is not convergent. So this is how the convergence factor looks like. So these are the convergence curves that you'll see very, very often in Martin's paper and in his collaborators' paper. This is a tool that we like a lot because it's very easy to understand, and it's also very revealing about the convergence of the Schwartz type algorithm, right? You just apply Fourier transform and you get the convergence factor, right? In the latest year, we have also, and Martins and other people developed similar techniques for bounded domains with Fourier series, but the principle is really exactly the same. So if you look here, this is the convergence factor depending on the frequency here. So you see that the higher the frequency, the faster, I mean, this closer to 0. So a row close to 0, that means the algorithm will converge very, very fast. Okay, the row close to 1 is not good. Row close to 0 is very good. Okay, so here some properties. So from this picture we can see there are a few interesting conclusions, right? So as I said, this is always bounded by 1. As soon as delta is strictly bigger than 0, this will tend to 0 as k goes to infinity because of this exponential here, okay? So we can infer that high frequency mode that the error will converge very, very fast. So suppose that in your error vector initially, you have only high frequency modes, yeah? So very highly oscillated modes, so sine of, I don't know, 1000x or something like that. So this will make the algorithm converge very, very fast. So I don't know if this reminds you of, stationary methods or Jacobi method, where in the Jacobi method, the higher frequencies are converged very, very fast, and lower frequency, they need more iteration to converge. So it's a very similar thing. As I explained you yesterday, Schwartz algorithm is morally like a block Jacobi algorithm. Okay, so that no overlap, no convergence, rho is equal to 1. So there is no mystery about that. Okay, so this is about the convergence. So as you have seen here two simple examples in which you really can compute and prove convergence of these algorithms. Now, if you change the equation, you can do similar things for different equations. We did for convection diffusion, for Maxwell, for Helmholtz. You can apply similar techniques. You can also add boundaries. You can have more domains. Obviously, you need some regularity, some very structured domains in order to do that, or infinite domains in which you don't care about the boundary conditions. Okay, so this is the second thing that I wanted to explain today. So I see that I am almost on track. So the third thing that I wanted to explain is the link between the link with Krylov methods, because I mentioned the idea of preconditioner, the Schwartz method as solvers and preconditioners, so I want to develop on this aspect. So I just keep, so this is just free-form implementation. Yeah, I want to mention that you can also, on my webpage, you can download the codes corresponding, yeah, that can do all these things, right? So I will try to explain how to use the Schwartz algorithm as preconditioners, right? So as opposed to a Schwartz algorithm as solvers, so what is the difference between solvers and preconditionals? So solver is just the iterative solvers that you have seen there. That is just the block Jacobi equivalent method, right? So this is an iterative solver, which is a stationary iteration, right? Preconditional stationary iteration. So this is the original Schwartz method. So now the thing is, this is very nice to explain, and it's very easy to understand, and it's also good to start with. But in practice, people will never use Schwartz method as pure solvers, because from your lecture probably, the stationary iterations are not good, okay? If you want to solve a large linear system, you won't use Jacobi, Gauss-Seidel, or something, just pure. For this, you want to do something more sophisticated and faster, right? So now how you can use the benefit of the domain decomposition, but also to combine this with a Krylov solver, okay? So I try to explain this idea. So in the first instance, I try to explain, if it's not obvious, probably it's obvious for a lot of you, probably not, but in any case, why stationary iteration is worse than a Krylov method, right? So here it holds, it can be explained in a very simple way. So let's take again our favorite system, Ax equal B, okay? So let's define a fixed point algorithm with a preconditioner fixed point algorithm. It can be any method, right? You can write Jacobi, Gauss-Seidel, anything, right? So this is a fixed point method, B is my preconditioner, right? So that means X here is in fact a fixed point of the operator that is defined on the right-hand side. Okay, so you can see this, this is a fixed point algorithm, right? So now let's rewrite this iteration a bit differently. So first let's define a residual. So R0 is the initial residual of my method, right? And here C, it's simply the preconditioned matrix, right? So this A is my original matrix and B is some preconditioner, right? So C is the preconditioned matrix. So now if you just write this iteration, so this is xn as a function of xn plus 1 as a function of xn, and if you just continue xn as a function of x minus 1 and you just go until x0, then you can write the solution as this sum, right? So it's a very simple exercise. You just keep computing matrices and you end up with here, yeah? So you can see that the xn, the iteration xn, is in fact identity minus c to the power I here. This is the preconditioned matrix, and it's the initial residual and initial iterate. So roughly speaking, you can express that as the initial guess, initial residual, and some matrices here, okay? So when does this converge? So you can see that this won't be convergent unless identity minus c, the spectral radius, is less than 1, right? If it's not less than 1, that means this will increase, keep increasing, so that means your method will diverge. So this is a very simple observation. Now, on the right-hand side, I will try to explain again with my hands what is the Krylov method, right? So again, you can see that this fixed point iteration, preconditional fixed point iteration, in fact, is equivalent at convergence by solving this preconditional linear system, b minus 1a equal b minus 1b, right? So again, you have this initial guess, you have initial residual, and here you have this initial error, right? So what is the, let's say, the idea, the rationale that stays at the basis of the Krylov methods is the following, is that if you have here C is my preconditioned matrix, and this is invertible, there exists also always a polynomial of a certain degree, such that the inverse is the polynomial of the same matrix, okay? So this is the idea that as a basis, lies at the basis of Krylov methods. Yeah, you can also build this kind of polynomial. So now what is the link between the two? Right? What is the link between the two? So if you look here a bit closer, you can identify here a polynomial of the matrix C somehow, right? So that means my constructive proof shows me that the solution here at the convergence is a polynomial of the matrix C, right? But the thing is, my fixed point method here will build me a polynomial of the matrix C, but with some fixed coefficients, and these fixed coefficients are given exactly by my fixed point method, right? So now to summarize, so if you just use a stationary iterative method, you build a solution. The solution, in fact, is a polynomial of the preconditioned matrix applied to some initial residual and depends also on initial guess, right? This polynomial has some fixed coefficients. So that means your stationary method will produce this kind of polynomial fixed coefficients. But now it's a bit more intelligent to say, what if I take all the polynomials up to a certain degree of this matrix, but with any coefficients, and then I minimize the error at each iteration in such a way that my residual is spanned by all the polynomial of this degree. So I don't keep the coefficient fixed anymore. I just allow any coefficient, and I just take the best coefficient that will minimize the residual, right? So this is the Krylov method. So you can see that if you keep fixed coefficient for this polynomial representation of the matrix, it's less optimal as if you optimize the coefficient at each iteration as the Krylov method do. Okay? So this is the, let's say, the main argument for which we use Krylov method instead of fixed point iteration because the residual is optimized at each iteration. Okay, so here you see that in fact it makes sense to say, in fact my residual is spanned, it lies in the space spanned by this power of the matrix, preconditional matrix, which multiply the initial residual, right? Okay, so this comes exactly from here. You see that this my residual, it will belong to the space, linear space spanned by these guys. Okay, so this is called a Krylov space. So that's why we seek for the solution in the Krylov space, because this is also something that you can see very easily with a stationary point iteration. So now let's give an example of a Krylov method. And how do you look for the optimal, let's say, representation, optimal iterate in the Krylov space here? So it's something that you probably already know, the conjugate gradient method. So conjugate gradient will be applied to symmetric positive definite matrices, and you want to minimize the norm of the residual. So you look for this W in the Krylov space defined here. But you need to minimize also this in a certain norm. And here, since the matrix is symmetric positive definite, you have a norm for free, so you can use the A-1 norm to minimize, and you get the perfect iterate, right? So this is the conjugate gradient. I'm pretty sure you haven't seen it this way, because it was not probably explained this way, but you can find a similar explanation, interpretation in Youssef Saad's book on the iterative methods. Okay, so this is the iteration. So let me show you how does it look like, the conjugate gradient, and why it's important for me to show you the conjugate gradient even if it's not about domain decomposition, because I will show you immediately after how do I insert my domain decomposition preconditioner into this story. Okay, so let's, I have 10 more minutes, so let's breathe 1 second. So I move on to conjugate gradient, and then I introduce my preconditioner there. So how do the conjugate gradient looks like? Right, so the conjugate gradient will compute iteratively a solution of the linear system, and by this recursion formula, which is very cheap. So why it's cheap, I explain it. So notations are usual, so x naught is the initial iterate, r is the residual, a is the matrix, and so on, right? So how does it work? So this is the iteration loop. I start by computing some 2 norm of the residual. Okay, I define some direction here, P1, right? And some other quantities. So why is this all cheap? Why do you see it's cheap here? Because roughly what you need, the most expensive operation here, it's the matrix vector product that you see here. You have only one of it. And then you need to update here the solution of the residual. And that's all, right? So it's a very, very cheap recursion formula. And this will optimize the, let's say, the iteration, for the solution at each iteration in the sense that I explained here. Okay, so this is the best method ever if you have a symmetric positive definite, because it guarantees you will converge in a best number of iteration. The only thing is, as I said, you can improve it by replacing the matrix here A by a precondition matrix, right? By a matrix C that contains a preconditioner. GMRS, I just keep GMRS. I just stay to the basics, right? So now, if I just go back 1 second, I try to go slowly, right? So if you look at this fixed point method, what does it remind you? This fixed point method. I don't know if I'm allowed to ask questions to see if you understood. So the fixed point method, what does it remind you? If you just replace x by u, this is in fact my Schwartz iteration, right? So this is the residual, and this is the preconditioner, right? So instead of b, you can imagine it's that m-1 RAS that is defined before. Sorry, I have too many slides, so going back it's a bit tricky. Okay, so in fact, instead of B, you can imagine this kind of thing, right? Or this one. Okay, and this comes from the domain decomposition. Okay, Okay, so that means this my Schwartz method in its iterative form, it's a fixed point iteration in which you have a preconditional, right? So now you say, if you look at these things, instead of using my Schwartz method, which is a fixed point iteration, I just move to the second panel. I use a Krylov method, but to the precondition iteration, right? So this is my matrix, global matrix A, and this B minus 1, it's simply the preconditional that comes from the domain decomposition. So all this to say, you forget about all the Schwartz iteration, the alternative version, parallel version, and so on, and you just keep from it the precondition part. Yeah, so the blocks of the matrices, the restriction operators, and the partition of unity, right? So if you have all these objects, partition of unity, restriction, that means you have a preconditional for free. So now that means you choose your favorite Krylov method. Is your matrix SPD, you take a conjugate gradient, and here you apply the conjugate gradient to your preconditioned problem. Okay, so now let's do that. So let's suppose that we use additive Schwartz as a preconditioner. So remember, additive Schwartz, it's like my initial restricted additive Schwartz method, but from which I remove the partition of unity. So why am I allowed to move the partition of unity? So in principle, I'm not allowed to do it when I use it as a solver, because I'm doing too many things in the overlap, so that means the method won't converge. But when I use it as a precondition, I can do whatever I want, yeah? Provided that the matrix is not very far from the initial one. Okay? And this is very attractive because this preconditioner is symmetric. If the matrix is symmetric, it's very good. I can use conjugate gradient. Okay, so now just to finish up, how can we insert it in the conjugate gradient? I don't expect you to remember the conjugate gradient because you will never have to code it. You have it in a lot of libraries for free. But suppose that you have your code, yeah, and your library, whatever. So in order to change your code to insert the Schwartz preconditioner, you just only need to insert it in several points, right? You just have your usual conjugate gradient and you insert your Schwartz preconditioner inside, yeah? Typically, you need it when you need to update the residual because you need to have preconditioned here residuals, right? So what is so another remark here? So that means if you want to solve AU equal B, and you have a matrix vector product, routine, that means you just need a preconditioner routine. You need the application of the preconditioner to some other vector, and that's it, right? You don't need to set another code, and then you introduce it in the parallel, sequential, whatever version of your Krylov method. Most of the, these libraries, PETSI and equivalent, they already have that. So now what I have here, this is probably something that you haven't seen under this form. So here it's an estimate of the convergence of the linear system with the preconditioner. So here is the initial error, which is computed in some norm here. It's a strange norm in which you have a symmetric version of the precondition matrix. Okay, so this is a norm of the initial error, the norm of the error at the iteration m. And here is the convergence factor. Okay, so the power m comes from the fact that I am at the m iteration. So you see that the convergence of the conjugate gradient depends on the square root of condition number. So this is the quantity that you need to improve to get closer to 1 by applying the Schwartz preconditional, right? There are a lot of other techniques to show that how this can be improved, and this is object of other things, but I don't have time to show it now. So now just to wrap up, I just show you again the curves of yesterday. Now probably it makes a bit more sense in light of what I just told you. So here I just solve a problem. This is the solution, probably is not very meaningful, of a Poisson problem with different kind of boundary conditions. Yeah, I just put different kind of boundary conditions everywhere. And then just apply I solve it by a Schwartz iterative method, right? So it's a purely iterative one, the fixed point iteration with the preconditioner. So as I explained, you have seen my little convergence study. So you expect that if you increase the overlap, the convergence will be better, right? Now there is a price to pay. The more overlap you have, the more redundant information you have between the domains. So it means the algorithm will be more expensive. So you need to find the trade-off between how much overlap you put and you know, how is the quality of your convergence, targeted convergence. But if you use the Schwartz method as a preconditioner, then this is a bit less sensitive to the overlap, right? And also the iteration count, it's far better, yeah? So we say in the sense that the Krylov methods will accelerate the convergence of the Schwartz method. And here we use the Schwartz as a preconditioner, right? So you need to keep in mind this dual nature of Schwartz methods. So Schwartz method as solvers, which are very nice to explain. It's very easy to start with, but which is something we'll never use in practice. And Schwartz method as preconditioner, in which we just extract the nice information provided by the decomposition. That means the local matrices, the restriction operators, extension operators, partition unity, to build a preconditioner for a Krylov method, right? The Krylov method being conjugate gradient, GMRS, and so on, okay? So, yeah, I think I'm just on time. So this is, I mean, it's probably, I wanted to tell you more, but I was probably over optimistic yesterday. So sorry if I went a bit too fast. But I can also make available the part 2, which I didn't have the occasion to present, if you want to have a look, which is about core spaces. Okay, so thanks a lot for your attention.